All right, this is AP BC Calculus. We're doing a BC only unit. This is Unit 10, Section 13. We're talking about the radius and interval of convergence of a power series, which is basically lots and lots of the ratio test. So what is a power series? A power series is any series of the form, the sum from n is 0 to infinity of c sub n, where c sub n is some constant, times x minus a raised to the n, where n is a non-negative integer, and c sub 0, c sub 1, c sub 2, c sub n are all real numbers, and a is also a real number. So here are some examples of power series. Here, this is my c sub n term. It's going to change with each n that I plug in, and they don't have to start at 0, right? Here I started at 0, but n just has to be a non-negative integer. So it could start at 0, it should start at 3, it could start at 10, doesn't matter. So I plug in the different n values, and basically what I get is this giant polynomial where there is some coefficient, so this would be c sub 1, and this would be c sub 2, and this would be c sub 3, in front of, in this case, an x plus 3 to a power, right? Here we have a different c sub n, right? We have 2 to the n over n, and that's going to make my constants, right, which are going to be 2 over 1, and 4 over 2, and 8 over 3, in front of this 4x minus 8 to the n. And you could simplify this so that it would look more like this, because I understand that it doesn't look like an x minus a, but for instance, what you could do here is you could factor out. If you're saying to yourself, oh, 4x minus 8 doesn't look like this, well, you could actually rewrite this as a 4 to the n times an x minus 2 to the n, and there's your power series that has the x minus 8 to the n, right? So the coefficients are all different, but they follow a rule, in this case, the rule for c sub n. All right, so when we want to find the radius of convergence for a power series, we're going to go back to what we learned in a previous video, and we're going to talk about the ratio test. So if a power series converges, it can be convergent either to a single x value or over an interval. We use the ratio test to determine the radius of convergence of a power series. Basically, we use the ratio test to get some x minus a inside an absolute value is less than r, and that r is called the radius of convergence. So let's go ahead and find the radius of convergence for a couple of series. So find the radius of convergence. When you hear this, oh, sorry, didn't mean to go through there. When you hear this, right, this means set up the ratio test. That's literally what this means. So this is saying set up the ratio test. So you're going to set up the ratio test, and you want this to converge, right? So for the ratio test to converge, you want the limit as n approaches infinity of a sub n plus 1 over a sub n to be less than 1, right? That's what you need, so in that absolute value. So let's go. This is what we're going to set up every single time we hear that, and we're going to get a point for it on the AP, and it's super duper important. It needs to be the limit as n approaches infinity, right? My a sub n plus 1 term is going to be a negative 2 to the n plus 1 times an x plus 3 raised to the n plus 1, all over a square root of n plus 1, divided by, and then my a sub nth term is going to be just this exact term, exactly as it's written, copied down again. Right, so I'm not going to change it at all. N plus, oh, I didn't mean the n plus 1, I just meant an n. Come on, sometimes my brain is tragic. All divided by a root n. We're going to clean that up, divided by a fraction. All right, so when we clean this up, we want this to be less than 1, but really you're just going to kind of save all the work and leave that less than 1 for the end. So when I clean this up, I'm going to get the limit as n approaches infinity. So I have a negative 2 to the 2n plus 1. I have an x plus 3 to the n plus 1. And then on the bottom of the fraction, I have a root n minus 1. Now when n plus 1. When I deal with this fraction, I'm going to flip and multiply by the reciprocal. So what's going to happen is the negative 2 to the n is going to be on the bottom. So is the x plus 3 to the n, right? And the root n will be on the top. That's what's going to happen every single time. So I want this whole thing to be less than 1, but we're going to get there in a sec. So when I clean this up, this is the limit as n approaches infinity. Well, this is a negative 2 to the n plus 1 over a negative 2 to the n. So I would subtract their exponents and just get that this is a negative 2 to the first on the top. Same thing here. I'm going to subtract these exponents, and I'm just going to get that this is an x plus 3 on the top, right? And then this thing, although it looks disgusting, is actually not at all problematic, because remember, we have this limit as n approaches infinity. Well, this is now the only term left that has any n stuff. The rest of the stuff doesn't have an n at all, right? So if we look at this, this is the limit as n approaches infinity of this thing, which we're going to deal with in just a sec, because that's the only thing left with an n, times this absolute value that we're going to deal with in just a minute. And that's less than 1. Well, these are n's with the same power. They're both an n to the 1/2, and the same leading coefficient is both a 1. So these guys are going to come out to be a 1. So I basically get that -2 times this x plus 3 inside an absolute value is less than 1. Well, inside the absolute value, this is the same as the absolute value of a -2 times the absolute value of an x plus 3, because it's all multiplication. So this is just a 2. So I'm going to get x plus 3 in the absolute value is less than 1/2. Well, that is my radius of convergence, because remember, it was x minus a is less than r. So my radius of convergence is 1/2, right? So in this situation, my a is a -3, right? So basically what we're getting is that if here is a, which is -3, -2 and -4, the radius of convergence from this spot goes 1/2 this way and 1/2 this way. The radius is 1/2 on either side of that center of -3. Now we're going to talk about what happens at the two ends in a minute. I think after one more practice problem, we're going to talk about the interval. But that's what this is saying. This is saying from this center, we could go out half this way or half this way, and that is our radius of convergence, right? So that's what you're asked to do anytime you're asked for the radius of convergence. Set up the ratio test, and then your answer should be x minus a is less than r. The answer that you want when you're asked for the radius of convergence is whatever this r value is. That's it. That's what's going to happen every time you're asked for the ratio test. Every time you're asked for the radius of convergence, it's the ratio test. So we're going to do this again. Find the radius of convergence, right? So that is code for set up the ratio test, right? Set up the ratio test such that this thing converges, and then your answer is going to end up looking like an x minus a is less than r, and you want this radius. That's 100% what you're being asked to do. So if I go ahead and set up this ratio test, the limit as n approaches infinity of a sub n plus 1 is going to be 2 to the n plus 1, x plus 2 to the n plus 1 divided by an n plus 1 plus 2 factorial, which we'll deal with in a sec. On the bottom, it's just going to be that a sub n exactly as it was written. I don't do anything but copy that problem down. All right, so I'm going to get that this is the limit. Oh, and I do technically want this to be less than 1, so you can throw that in there whenever you're ready. It can also just be something that you throw in at the end after you simplify a bunch of stuff. That's fine. So this is a 2 to the n plus 1, an x plus 2 to the n plus 1. And on the bottom, it seems to be an n plus 3 factorial, which we'll deal with in a sec. This bottom fraction, right, because I'm dividing by a fraction, it flips, and so the stuff that was in its numerator ends up in the denominator. It's not an accident. We saw this in our ratio test problem as well, or in our ratio test section as well, right? It's not at all an accident that what's going to happen is everybody has a partner. The 2 to the n plus 1 is partnered with the 2 to the n, and that's not a surprise at all. So these guys are going to simplify. So I'm going to get that this is the limit as n approaches infinity. These guys just simplify to a 2. These guys just simplify to an x plus 2, right? And these guys are going to simplify because this is actually an n plus 3 times an n plus 2 factorial, right? Because that would mean, so that's what this is. Well, these guys cancel, and I just get that this is a 1 over n plus 3. I want this to be less than 1. Well, the trick here is the only thing left that has an n is this guy, right? And there's only an n on the bottom. So the limit as n approaches infinity of 1 over n plus 3 is totally a 0. So it doesn't actually end up mattering, right? It doesn't actually end up mattering that I have this other stuff, because this is definitely a 0. And 0 times all this stuff, regardless of what the stuff is still totally 0. So 0 is less than 1. That is literally always true. So my radius is infinity, right? What this is saying is this converges for all x. Right? This converges for all real numbers x, right? So, so the radius in this case, because I ended up getting 0 is less than 1, that is always true. So my radius is infinity. Now let's talk about an interval of convergence. So if you go back up to here, notice that in this picture I drew, you had some center, which in this case was -3, and then the radius said I could go 1/2 unit in either direction, right? Well, the interval of convergence is that window from one of those open circles that I drew to the other. So this would be the interval of convergence. The question is, what happens at the two ends? What happens at -3.5 and what happens at -2.5, right? Does this series converge or diverge? And so that's what we're going to deal with when we talk about the interval of convergence. Applying the ratio test gives you the radius, and that allows you to find the open interval on which the series converges. But in order to find the entire interval, you have to test both endpoints separately to determine if the series converges or diverges at those endpoints. Generally, when you plug in the endpoint for the values for x, you're going to get a really familiar, specifically memorized series like the harmonic series or another p series. You should know from memory, in general, if the series you get converges or diverges. Sure, there could be a really tricky question where you don't get one of the memorized series, but it's pretty unlikely. So let's go ahead and walk through this. When we're asked to find the interval of convergence, now this has a little bit of different stuff. The first thing this is telling us is to do the ratio test. So that's going to find the radius for us, right? So the first thing, ratio test to find the radius of convergence. 2, that gives us the open interval around whatever a is, x equals a, because remember, we're looking for x minus a is less than r, right? The endpoints are going to be that center plus or minus r. So either a plus r or a minus r, right? The center plus r, the center minus r, right? We're going to check the endpoints individually. So we're going to check each one to see if it makes a convergent or divergent series. All right, and I'm going to walk you through that, but that's what, when we hear interval of convergence, that's what has to happen. The same steps as radius of convergence, but then after that we have to look at the two endpoints separately. So let's go ahead and walk through this. The first step is that we need the ratio test. So I need the limit as n approaches infinity of a sub n plus 1 over a sub n to be less than 1. Well, that is going to be the limit as n approaches infinity of, so this is going to be a negative 1 to the n plus 1, right? X minus 3 to the n plus 1, and a 2 times n plus 1 all plus a 1, all over negative 1 to the n, x minus 3 to the n, and a 2n plus 1. And I want that to be less than 1. Now the first sort of hint you'll start to see with this is the negative 1 is irrelevant, because since it's in the absolute value, I am going to end up with a negative 1 in here, but the absolute value is going to completely knock that out. It won't matter at all. So I get an x minus 3 to the n plus 1. On the bottom, I'm going to have this. So this is a 2n plus 2 plus 1. So that's a 2n plus 3, right? This fraction all gets flipped. So the negative 1 to the n lands on the bottom. The x minus 3 to the n lands on the bottom. And the 2n plus 1 lands on the top. But again, not a shock, because we can see that everybody's matched up with their buddy, right? These guys are going to cancel to net a negative 1, which again, in the context of this problem, doesn't matter because it's inside an absolute value. These guys are going to net a an x minus 3 to the first, right? And then these guys don't cancel, but remember, n is approaching infinity. So as n approaches infinity, in fact, we can see that the only part of the limit that still needs this thing, right, that still needs the limit at all, is the part with the n's, right? And then again, this part doesn't really matter, so I'm going to get an x minus 3 is less than 1. Well, these guys, as they approach infinity, they have the same degree and the same leading coefficient, which means this thing is a 2 over 2 or just a 1. So I get 1 times this absolute value is less than 1. Well, that's my formula. X minus a is less than r, right? So my a is 3. My radius is 1. So the interval that I'm looking at, so the open interval, right? The open interval is basically, here's 3, right? I can go 1 unit this way, that would be 4. I can go 1 unit this way, that would be 2. So that's my open interval, right? The open interval is 2 to 4. I now have to check the ends. So I'm going to check the ends. So my end points are x is 2 and x is 4. So if we go back up and look at the original series, and I'm going to actually probably take a screenshot and drag it down because I'm feeling a little bit too lazy to recopy it right now. So if I take this down here, all right, and we'll drop that right there for convenience, right? So that's my open interval, and we'll actually move it a little bit farther down so we can see it a little easier. All right, so let's check the endpoints. So I'm going to plug in both of those x values and see what happens. Well, when I plug in x is 2, oh, my bad. All right, when I plug in x is 2, what's going to happen is if x were 2, this is going to be the sum from n is 0 to infinity of negative 1 to the n. When I plug in 2, I get 2 minus 3. So that's a negative 1 to the n over a 2n plus 1. Well, that's a negative 1 to the 2n. Remember that 2n is an even number. So that's just going to be a 1, right? This is going to be essentially very similar to the harmonic series. Now, I did tell you that most of the time it's going to be a memorized series. In this case, it's not a memorized series, but because this is similar to a p-series, right? This is essentially, this is very, very similar to a p-series. You could use limit comparison. You could use the limit comparison test to find that essentially this behaves like 1 over n, which we know diverges, right? And again, most of the time you get a much more familiar series, of course, because I specifically told you that on the first example you didn't, and it happens. When we plug in 4, I'm going to get the sum from n is 0 to infinity of a negative 1 to the n times a 1 to the n over 2n plus 1. Well, this one is going to converge. Sorry, there's my sigma. Because this, if we look, this is an alternating series, right? And remember, if you're an alternating series, all that you have to show, so if this negative 1 is the alternating piece, then this is the b sub n, right? So if this is my b sub n, it is decreasing, and you could see that as you pick bigger and bigger values of n, and it is approaching 0 if you pick as n approaches infinity. So this thing converges by the alternating series test. What that means is that my final answer is going to be that the interval of convergence is going to be not including 2, but it is including 4. Or the other way to write it is 2 is less than x is less than or equal to 4. Okay, I prefer parenthetical notation. Again, the trick is that for the 2, you would technically have to do the limit comparison test. But in this instance, like as you get more comfortable with it, you're not necessarily going to be required to show which test you use. You just need to know if it comes out as convergent or divergent. So let's try another one. All right, so we're going to find the interval of convergence for the power series. So again, remember, this means the first thing you're going to do is find the radius of convergence by setting up the ratio test. So my a sub n plus 1, negative 1 to the n plus 1, x to the n plus 1 over n plus 1, right? Divided by a sub n, which just means copy the a sub n exactly as you have it. And that whole thing should be less than 1. So this is the limit as n approaches infinity of a negative 1 to the n plus 1, x to the n plus 1, and then an n plus 1, because that bottom fraction will get flipped. And then this will be a negative 1 to the n, an x to the n, and an n plus 2. So as we've seen every other time, everybody has a matching buddy and things cancel. So this is going to cancel to a negative 1, but I don't really care about that because it's inside the absolute value. This will just be an x, right? And then this is honestly the only part that I care about the limit for anymore because nobody else has an n anymore, right? The only thing that still has an n is the n plus 1 over the n plus 2. So this limit only really pertains to this, and that's definitely a 1 because the n's have the same power. So I end up getting the absolute value of x is less than 1, meaning this is x minus 0 is less than 1. My center is at 0. My radius is 1. So the interval I'm looking at is from 0 up to 1 and down to negative 1. That's my interval that I'm looking at. So the open interval is negative 1 to 1. So then I have to check the n's, right? So we're going to check the n's. I have to check x is negative 1. I'm going to have to check x is 1. And let me just go ahead and drag a copy of that function down so we don't have to do it from scratch because that seems more sensible. So checking the endpoints. So, and I think you kind of get the gist of this as you work. So if you plug in negative 1, this is going to be the sum from 0 to infinity of a negative 1 to the n times a negative 1 to the n over an n plus 1. We've already seen that this becomes a negative 1 to the 2n, which is really just a 1, right? Because that's an even power. 2n is an even power. So this thing is actually the series from 0 to infinity of 1 over n plus 1. This diverges because this is essentially the harmonic series, right? It might not look like the harmonic series when you know, because it doesn't just have the n, it's not 1 over n, but this is basically 1 over n, right? In fact, it's 1 over n where you just shifted and started at 0. So this is 1 plus 1/2 plus 1/3. This is definitely the harmonic series, and it definitely diverges. When I plug in the 1, right, I'm going to get the sum from n is 0 to infinity of a negative 1 to the n times a 1 over an n plus 1. Well, this is the alternating harmonic series, right? It doesn't really matter that it starts at 0 because they just started with an n plus 1 instead of an n. But this is the alternating harmonic series. It's going to start out as a 1 and then a negative 1/2 and then a plus 1/3. That's definitely the alternating harmonic series, and it definitely converges. So my answer is parentheses negative 1 and then a 1 with a bracket. Or if you prefer, negative 1 is less than x is less than or equal to 1. All right, let's try another example. So we're going to find the interval of convergence for the power series. So that means go ahead and start with your ratio test. And there's a little bit of a trick on this one that we'll talk about after. But if we start with our ratio test, this is going to be the n plus 1th term, right? So a sub n plus 1 over a sub n. Cool. All right, so we get that my n plus 1th term over my nth term is less than or equal to 1. There's not a ton of simplifying that you can do here. Basically, you're going to simplify the x power. So you're going to get this limit, right? And then the x powers actually just become an x, right? Because it's n plus 1 minus n. So this limit, as n approaches infinity, this thing's going to go to a 1. So I'm just going to get the absolute value of x is less than 1. So that's the same as x minus 0 is less than 1, meaning my center is 0 and my radius is 1, right? So as we've seen before, right, I'm looking at this window here. Right, so the question is, what do the ends do? This thing definitely converges in the middle. What do the ends do? So I'm going to test the ends. All right, so if we pick x is negative 1 and we pick x is 1, right, those are my two endpoints. So this is going to be the sum from n is 0 to infinity of the square root of n times a negative 1 to the n, right? And this is going to be the sum from n is 0 to infinity of the square root of n times a 1 to the n. Well, both of these are going to diverge. Here's why. Let's start with the, well, yeah, let's start with either of them. It doesn't really matter. In both cases, when a sub n approaches infinity, or when n approaches infinity, these aren't 0. If n's a big number and you multiply it by a 1 or a negative 1 to any power, it's not going to matter. It's not 0. So these diverge. So both, in both, that's not how you spell the word both diverge by the test for divergence. So basically what's going to happen is your answer ends up being the open interval, right? So your answer is just negative 1 to 1. Or if you prefer, you could write negative 1 is less than x is less than 1. So this only converges for the window between negative 1 and 1, not the two endpoints. All right, you're going to go ahead and find the interval of convergence for this power series, because you can see this is a trend. We're just going to keep doing this. So I'm going to find the limit as n approaches infinity. My a sub n plus 1th term looks like this, right, over an n plus 1 to the 3rd. And my a sub nth term is a 10 to the n, x to the n over an n cubed. Just to point out, because some of you might be saying, Hogan, I can see what's going to happen. Do I have to keep writing this as a ratio? Write it as a ratio once, because the AP is going to give you a point for the limit and a point for that it's a ratio. If after that ratio you're able to jump to everything else in your head, that's great. Congratulations, I'm not judging, right? If you're able to say, hey, you know what, Hogan, I get it. I get exactly what's going to happen. I've seen this a million times. Great. That's your business, right? And I'm not going to disagree, because I think, like, quite often I can do the same thing, right? But you want to make sure you're communicating understanding by setting up the ratio test once correctly. And then if you jump to simplifying without showing a ton of work, that's your business, right? So if you were able to look at this and in your head be like, oh, I get it, it's going to be a 10x, that's great. Congratulations. Awesome. I'm not judging you. So if you were able to look at that and say, hey, this is a 10 and an x, and then because this is an n cubed over something that is clearly also going to be an n cubed, like if you foiled this out, this would be n cubed plus a bunch of stuff, right? They're both n cubes. So if you can spot that that's going to become a 1, Oh, and for the record, if you know Pascal's triangle, you know this is n cubed plus 3n squared plus 3n plus 1. When I say plus a bunch of stuff, I'm not negating the fact that I actually know how to FOIL out n plus 1 quantity cubed. I'm pointing out that it's irrelevant, right? So this definitely, this definitely becomes a 1. Once you know that, you've got a 10x is less than 1. So that's an absolute value of x is less than 1/10, right? So you're looking at x minus 0 is less than 1 over 10. That means that this is your center and this is your radius, right? So you're going from 0 over 1/10 unit or over 1/10 unit the other way, right? Those are your two endpoints. These are the two things you have to look at. So now when we consider the endpoints, and you do have to consider both endpoints, that's important. The AP is going to be looking for it. You're going to consider x as negative 1/10, and you're going to consider x as 1/10, right? So let's go ahead and grab our series so that I don't have to copy it down because I'm lazy. All right, so there's our series. So let's consider it at both ends, right? If I plug in negative 1/10, so this is going to be the sum from n is 1. Oh, both of these converge. This is a 10 to the n, negative 1/10 to the n over n cubed. Well, if you clean up this, since it's all to the n, right, this numerator is the same as a negative 10/10 to the n, which would just be a negative 1 to the n. So this is a p-series that would have converged even if it wasn't alternating, right? Like this is a p-series. This would have converged absolutely, meaning it would have converged even if it was positive only. So it's definitely going to converge when it's alternating. So this definitely converges, which is why when I got that in my head, I was able to say, oh yeah, they both converge, because I know that this one's going to come out exactly the same way, but without the alternating sign, right? So this is going to be 10 to the n and a 1/10 to the n over an n cubed. Well, this is just going to be a 1 over n cubed, but that's a p-series. That's going to be a p-series that converges, right? This is a p-series that would converge whether it was positive or not. So this also converges. So my answer is going to be negative 1/10 in a bracket to 1/10 in a bracket. Or if you're not a parenthetical notation person, you could have said negative 1/10 is less than or equal to x is less than or equal to 1/10, right? Either of those would be fine. All right, let's do another one. We're going to find the interval of convergence of the power series. So we're going to go ahead and set up our limit as n approaches infinity. Our a sub n plus 1 term is going to be n plus 1 factorial times a 2x minus 1 to the n plus 1, right? On top of n factorial and then 2x minus 1 to the n, and that should be less than 1. So remember, and this is an important thing about factorials because it is kind of key to understand how they work, that n plus 1 factorial is just n plus 1 times an n factorial. So those n factorials are going to cancel. I'm going to get that this is the limit as n approaches infinity of an n plus 1 with nothing on the bottom to cancel it out times a 2x minus 1 is less than 1. So what's happening here is this is going to be infinity is less than 1, which is a lie, unless 2x minus 1 happens to be 0, which would be when x is a half. So this thing converges literally only for the point where x is 1/2, because at the point where x is 1/2, this thing sums to 0 plus 0 plus 0 plus 0 plus 0 plus 0 plus 0. So this only converges for the point x equals 1/2. That's it. It doesn't converge for any other values. There are no endpoints to test. The only time this converges is when this thing, right? So this is an infinity unless this thing were 0. And the only way that thing is 0 is if 2x minus 1 is 0. All right, so this one's a little bit tricky. Let's go ahead and find the interval of convergence. So we're going to set up the limit as n approaches infinity and set up our ratio test. So we're going to get an n plus 1 to the n plus 1 times an x to the n plus 1, right? That's my n plus 1th term. And then on the bottom, I have the n to the n times the x to the n. So here's why this is tricky. These two, the n expressions, don't have the same base. So while these two can be combined to simplify, right, I can't do that with the n's. And that's a bit problematic. But we're going to talk about that in just a sec. So n plus 1 to the n plus 1 over n to the n, right? And then this will just be times an x is less than 1. So here's the short answer, because you can't, so you can't distribute. This is not an n to the n plus 1 and a 1 to the n plus 1. That's not how that works. But if you were to FOIL this out, right? So if if you foiled this crazy, like infinitely large, right? If you foiled this infinite list of n plus 1s, right? Because it's n plus 1 times n plus 1 times da 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 da, if you foiled. The very first term is going to be an n to the n plus 1, right? It would be this thing to the highest power that you have to offer. The reason that's relevant is on the bottom I have an n to the n, right? The bottom is an n to the n, and the top is an n to the n plus 1 plus a bunch of stuff I don't really care about, because all I care about when I talk about limits as n approaches infinity are the leading terms. This power is bigger than the bottom power, meaning that this thing is going to be infinitely large. So, just like we saw in the last example, this thing is going to be infinity times x is less than 1. Well, that's only true, right? This is only possibly true if this x value is 0. So this thing is only going to converge, right? So this only converges for the point x equals 0. It doesn't converge anywhere else, because any other number you put here would be infinity times that number, and if you multiply infinity by any number that's not 0, you get something infinitely large. So there you have it. All right, let's do an E5 and a P5, and then we're going to segue into something a little bit different. So find the interval of convergence. And you'll notice we've done a ton of these because they're going to happen on your AP and you want to be good at it. So the limit as n approaches 0 of my n plus 1th term. And again, you can basically kind of cheat at this point and recognize that realistically you're going to be ignoring that negative 1 to the power, because you are. And this would be a 2 times n plus 1, all factorial, which we'll deal with in a sec, divided by, and then I just copy this thing on the bottom. So again, I'm kind of going to cheat at some point and recognize that I don't really care about that negative 1 to the power, because I know that coming out of this absolute value can't be something negative anyway, so it's not really relevant. So if we clean this up a little bit, I'm definitely going to get a negative 1 to the n plus 1 on top of his matching buddy on the other floor, right? I'm going to get an x to the 2n plus 2, because I'd have to distribute. So if we go back up here for a sec, this would be 2n plus 2, right? Divided by an x to the 2n, right? And I'm going to get, on the bottom, this will be a 2n plus 2 factorial. So 2n plus 2 quantity factorial. And on the top, it was just a 2n factorial, right, is less than 1. So now let's cancel a bunch of stuff. These guys technically cancel to a negative 1, but nobody cares, right? Nobody cares that there's a negative 1 there because it's inside this lovely absolute value. So I'm basically just going to ignore it. So I get that this is, these guys become an x squared, right? Because it would be 2n plus 2 minus 2n. And then this is a little bit tricky. So this is a 2n plus 2 times a 2n plus 1 times a 2n all the way down to the bottom. So these guys are going to cancel, and I'm going to get a 1 over a bunch of n stuff. Oh, sorry, this was as n approaches infinity. Sometimes my brain is slow. Okay, so it doesn't actually matter what's on the bottom, because the trick is that that's definitely going to be a 0, right? So as n approaches infinity, this thing is going to approach 0. So essentially, we get 0 times x squared is less than 1, and that's going to be true for all x. True for all x. So this thing converges from negative infinity to infinity, right? Or you could say converges for all x, right? It converges no matter what, okay? Let's do one more. All right, so we're going to go ahead and set up our ratio test. The limit as n approaches infinity of, so when I plug in n plus 1, right, it's a 4x plus 1 to the n plus 1 over an n plus 1 quantity squared over a 4x plus 1 to the n over an n quantity squared, right? And I want that less than 1. Sorry that I'm always really bad at making that one bar go too far. This is the limit as n approaches infinity. So I'm just going to group my stuff together, right? I recognize the n squared is going to be on top of this n plus 1 quantity squared. I recognize the 4x plus 1 to the n plus 1 is going to be on top of the 4x plus 1 to the n. So these guys are both n squareds, right? Like if I distributed, this would be n squared plus 2n plus 1. They're both n squareds, which means as we go to infinity, that's going to be a 1, right? And this is just going to be a 4x plus 1 is less than 1. But in order to find my radius of convergence, I'm supposed to write this so that this x is all by itself, right? So what I'm going to do is I'm going to factor out a 4. This is a 4 times an x plus 1/4, right? If I factor out that 4 is less than 1, right? So I get x plus 1/4 is less than 1/4. So my center is negative 1/4, and my radius is 1/4, right? So what we're looking at is here's 0, here's 1/4, here's negative 2/4, sorry, negative 1/4. So this is my radius, right? It's a 1/4 in either direction, right? So I'm basically testing my endpoints, right? So I'm going to test the ends. Well, the two ends are 0, right? So and negative 1/2. So I test x is negative 1/2, and I test x is 0, right? Cool. So when I do that, let's go get the series from the top because I'm too lazy to write it. So we scroll down to the bottom. We'll just drag this series in here. So we're going to test our endpoints, right? So I would argue that they're about the same amount of work. And again, we're going to see the same thing we've seen a couple times now, that you're going to get one of them to be, both of them are going to converge actually here because of the n squared on the bottom. So when I plug in negative 1/2, but they're going to be the same series. One is going to be alternating and one is not alternating. So when I plug in negative 1/2, right, I get a negative 2 plus 1 to the n all over an n squared. Well, that's a negative 1 alternating on the top over an n squared, which is definitely gonna converge, right? This is a p series where n is where p is 2 rather. This converges. It converges whether it's positive or negative. It happens to converge because it's alternating, but that gives me a pretty good idea that this one, which is not going to be alternating, is also going to converge, because this would be a 1 to the n over an n squared, right? So that's a 1 over n squared. And that definitely converges by the same reason, right? It happens that this one is alternating, right? But because this thing converges absolutely, right? So this thing converges absolutely. It would converge whether I was alternating or not. I don't have to worry about it, and both ends are going to be included. So my answer is going to be that both the negative 1/2 and the 0 are included. Or you could write it as negative 1/2 is less than or equal to x is less than or equal to 0. All right, so let's learn a couple quick new skills, and that'll be the end of this pretty lengthy video. All right, so recall that way back in AB, when we learned to differentiate, we learned that you could differentiate a polynomial term by term. For instance, if we had x to the 5th plus 3x to the 4th minus 10x to the 3rd plus 6x squared minus 9x plus 4, we could differentiate and get 5x to the 4th plus 12x to the 3rd minus 30x to the 2nd plus 12x minus 9 plus 0. Well, differentiation of a power series, which is just a polynomial with infinite terms, works the same way. We can differentiate a power series term by term as well. So if I have a power series that is some c sub n, which is just a coefficient, right, times x minus a to the n, if I want to differentiate it, right, I can do that by dropping the power down in front and lowering the power down by 1, right? So I get n c sub n, and then instead of being x minus a to the n, it's x minus a to the n plus 1, or sorry, minus 1, my bad. Sometimes I can't read. And if I list all these terms, you can see that if I differentiated my c sub 0, it would be gone because it's a constant and it's gone. If I differentiate c sub 1 times x minus a to the first, the 1 drops down in front and then the x minus a is gone. Oh, look, that's just c sub 1. If I differentiate moving forward, that's what happens. So let's go ahead and differentiate. So given the power series here, we're going to write the first 3 non-zero terms and the general term for this power series, the one that I'm given, f of x, and then we're going to differentiate it to find the power series for f prime of x. So for a, the power series is going to start when n is 1, right? So this power series, right, so my f of x is going to be equal to, when I plug in n is 1, I'm going to get x minus 2 to the first over a 5 times 1. So I'm going to get x minus 2 to the first, and then over a 5 times 1, but I'm gonna go ahead and say 1/5 in front because that's easier, right? So it's easier for me if I rewrite this as this thing in the front times this, and that's what I'm going to do, right? When I plug in n is 2, because I started at 1, when I plug in n is 2, I'm going to get that this is a 1 over 25 times 2, so that'd be 1 over 50, right? And then x minus 2 to the second, right? And then when I plug in n is 3, right? When I plug in n is 3, I'm going to get that this is a 1 over a $1.25 times 3, which I think is 375, so 1 over 375, right? And then x minus 2 to the third. And then I was asked to write the general term, so I'm going to do plus dot dot dot, and the general term is literally just the term that I was given, right? This is the general term, and then I'll put my dot, dot, dot to show that it keeps going, okay? Then I'm asked to differentiate and write the first three non-zero terms. And the only part of this that's a bit of a headache is that I'm going to have to write one more term here, and we'll talk about that in a sec. Oh, actually, I won't. I lied, because the first term's not going to go away. So my f prime of x, when I differentiate this guy, right, I drop the power down, right, 1/5 x minus 2 to the 0, but I just don't bother to write that, so it's just a fifth, right? When I drop the power down here, I'm going to get a 2/50 x minus 2 to the first. When I drop the power down here, I'm going to get a 3/375 x minus 2 to the second. So there's my first three terms, and then the general term, right? The general term, I'm going to drop the n down, and I'm going to get n over a 5 to the n times n, and then x minus 2 to the n minus 1. So if I clean that up a little bit, I get a 1/5 plus a 1/25 x minus 2 plus a 1/125 x minus 2 to the second plus dot, 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 dot. These n's can be canceled, and I get over 1 over 5 to the n x minus 2 to the n minus 1. Right, so again, carefully follow the instructions, but make sure you write however many terms are requested, right? If they say the first three non-zero terms, make sure you write 3, not 2, not 4. Write exactly what you're asked to write. Carefully follow the instructions, and as complicated as this looks, this is basically the same as differentiating a polynomial. All right, so let's try a P6. Give this a try. You're given the series for f of x. I want you to write the first three non-zero terms and the general term. Then I want you to differentiate. I want you to differentiate to find the first three non-zero terms and the general term of the power series for f prime. So for a, right, my f of x, notice that I am being clear which series is which, right? If you go back a slide, I was very clear that this was f of x and this was f prime, right? Make sure you're clear which function you're describing, because not being clear is going to cost you points. So I'm starting with n is 0. When I plug in n is 0, I get a positive 1. I get an x plus 1 to the 0, which is just going to be gone, right? And on the bottom, I seem to get a 2, right? And we'll clean that up in a sec. When I plug in n is 1, I get a negative 1. I get an x plus 1 to the first. And I seem to get, when I plug in 1, I get a 5 on the bottom, right? And you might find it easier to write it like this, where this is your coefficient, and then here's your x plus 1 to the n, right? That's your coefficient right here, okay? And when I plug in n is 2 for the next term, right, I'm going to get a positive 1, x plus 1 quantity squared, over, when I plug in 2, I should get 6 plus 2, so 8, right? Plus dot, 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 and then my general term is really just what I was given, right? It's a 3n plus 2, x plus 1 to the n, dot, dot, dot. Okay, if I clean that up a little bit, I have a 1/2 plus this negative 1/5 x plus 1, right? Plus a 1/8 x plus 1 quantity squared, plus dot, 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 this negative 1 to the n over 3n plus 2, x plus 1 to the n. Okay, so that's my f of x. Now when I differentiate, and this is one that I started to say in the last example and that didn't end up being an issue, the only thing that's a pain here is you're going to only get 2 terms when you differentiate. You're going to have to find one more term here. So when I find f prime, unfortunately, this first term derives to 0, which means I need another term. Right? I need one more term because I was asked to find the first 3 non-zero, and this one is 0. So we'll get to that in a sec. When I differentiate this guy, I just get the negative 1/5, right? Because the x to the first power drops down, and then I get an x plus 1 to the 0. So I just get a negative 1/5. This is going to be a 2/8 x plus 1 to the first. And then unfortunately, I need one more term before I get to my general term. So even though I didn't need another term up here, I kind of need one more term. So the fourth term of f, right, if I plugged in, so I plugged in n is 0, 1, 2. If I plug in n is 3, right, that fourth term would be a negative 1, x plus 1 to the third, over, this would be a 9 plus 2, so that would be an 11, right? So I get a negative 1/11. So if I know that's a negative 1/11, x plus 1 to the third, I can differentiate and get negative 3/11. So this is negative 3/11 x plus 1 to the second. So that's the other mystery term that I didn't need in part A, but I need in part B. And then my general term, dot, 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 when I drop this n down in front, I'm going to get a negative 1 to the n times n over 3n plus 2, and then x plus 1 to the n minus 1. And that's it, right? So I'm writing my first 3 non-zero terms, 1, 2, 3, and the general term. Notice I clearly communicated which function was which in both parts of my problem. So integration works exactly the same way. So if we recall that way back in AB, when we learned to integrate, we learned that you could integrate a polynomial term by term, right? So if I asked you to integrate some g of x that was x to the fifth plus 3x to the fourth minus 10x cubed plus 6x squared minus 9x plus 4, you would integrate the x to the fifth and get an x to the sixth over 6. You'd integrate the 3x to the fourth and get 3/5 x to the fifth, right? You'd integrate the negative 10x to the third and get a negative 10/4 x to the fourth, and so on, right? Plus that c for the constant integration. So when we integrate a power series, it's the same thing. We just integrate on a term-by-term basis, and we can integrate the general term the same way. Now, very often this c ends up being 0, and we'll talk about that when we move forward, but you do still have that constant of integration. So let's go ahead and practice integrating a power series. So when we integrate a power series, right, we're going to write the first 3 non-zero terms for f prime of x, which is what we're given, and then we're going to try and write the first 3 non-zero terms and the general term in the power series for f of x, given that we know f of 4 is a negative 1. All right, so let's start with a. So I'm starting where n is 0, and I'm going to go ahead and plug in. So my f prime of x, if I plug in n is 0, I'm going to get a 0, right, as the first term, because there's an n on top. So I'm just going to get a 0, so that one doesn't help, right? That was when n is 0. If I plug in n is 1, I'm going to get a 1 over 2, right? So the next term is a 1 over 2 x minus 4 to the first. So that's my first term, right? Then I'm going to get, when I plug in n is 2, right? When I plug in n is 2, I'm going to get 2 over 4. So you can leave it as a 2 over 4. You can make it a 1/2. I don't really care. X minus 4 to the second, right? When I plug in n is 3, right, I'm going to get 3 over 8 x minus 4 to the third, right, plus, and then, so notice, first 3 non-zero terms, 1, 2, 3, did it. General term is exactly what I was given, n over 2 to the n, x minus 4 to the n, plus dot, 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 right, because it's an infinite series. So when I go to do b, I just have to integrate each one of these terms, right? So when I integrate, so you can put the arbitrary constant at the beginning or the end. I will say that it usually makes the most sense to put it at the beginning, because when you look at a power series, it goes in the reverse order of most of the series you've learned, or I'm sorry, of most polynomials you've learned. Normally you list a polynomial with the highest degree first, but because for these series you can't ever have the highest degree because it's as n approaches infinity, you start with the lowest degree. So this thing's going to integrate to some arbitrary constant c that I don't know. When I integrate this, I'm going to up the power by 1, so it was to the first, now it's going to be the second, and divide by the new powers. This is going to become a 1/4 x minus 4 to the second, right? If you want to leave this as a 2/4, you certainly can, it doesn't matter. You could also, if you want to call this a 1/2, you certainly could, it doesn't matter. Same thing, I'm going to up the power by 1, so now it's cubed, and divide by that new power. So this is going to be a 1/6 x minus 4 to the third, right? Now, I was only actually asked to find the first 3 non-zero terms. So if we assume that c is not 0, I could stop. I'm going to be safe, and I'm going to find one more term in case c is 0, because if I plug in and find that c is 0, then I'm going to be really, really surly. I can tell you right now that c is not 0, but let's say, just to be safe, I'm probably going to integrate this guy too. So this would be an x, this would be a fourth, right? So I'm going to get that this is 3/32 x minus 4 to the fourth, and then when I integrate the general term, right, I'm going to up the power by 1, so that'd be n plus 1. So this is an n over 2 to the n times n plus 1 times x minus 4 to the n plus 1, right? Up the power by 1 divided by the new power plus dot, dot, dot. Now I need to find c. The way I'm going to find c is with this information. I want you to notice that it's not an accident that you were given 4. When x is 4, all of those infinite terms are 0, right? The x minus 4 to a power terms are 0 because x is 4. So what happens is that if f of 4 is a negative 1, all of these terms got knocked out, and the only thing left was a negative 1. Oh, hey, that c has to be a negative 1. So it turns out that I don't need that fourth term because c wasn't 0. So my answer to b is that f of x is a negative 1 plus 1/4 x minus 4 to the second plus 1/6 x minus 4 to the third plus dot, 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 n over 2 to the n, n plus 1, x minus 4 to the n plus 1. And that's it. All right, let's try one more. So Same thing, you're going to write the series for f prime, and then given some information, you're going to go ahead and write the series for f of x, right? So for a, right, for f prime, I'm going to write the beginning of the series out by writing the first three non-zero terms. So starting at n is 1 here, right? So when I plug in n is 1, I'm going to get a -1, an x to the first, and a 5, right? Oh, and again, remember, it's a little bit easier if you write your coefficient out in front like this. You'll probably find that easier, and then your x to the n is next to it, right? When I plug in n is 2, I'll get a +1, x to the second, over a 5 times 4, so that'd be a 20, right? When I plug in n is 3, I'm going to get a -1, an x to the third, and then a 45, right? Because it's 5 times 9, plus dot, 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 dot. And then I end up with a general term of -1 to the n over 5 to the n squared. Sorry, 5 multiplied by n squared, my bad. X to the n, dot, 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 dot. Okay, so there's my f prime. If you want to clean it up a little bit, you certainly can. You might want to write this as a -1/5 x plus a 1/20th x squared minus a 1/45th x cubed plus dot, 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 this -1 to the n over 5 n to the second x to the n. That's fine, right? When you go to do b, right, you're going to integrate on a term-by-term basis, right, when you find the antiderivative. So you still have the c, even though there's no original term there, you still need the constant because you're integrating, right? So when you integrate this guy, you're going to up the power by 1 and divide by the new power, so that's going to be dividing by 2, right? So that's a 1/10 x to the second, right, and it's negative. This is going to be a cube, so you're going to have to divide by 3, so that's a 1/60th x to the third. And again, if c is non-zero, I don't actually need this next term, but I'm not sure yet, so I'm just going to go ahead and up this to 4, right? 4 times 45 should be a 180, so this is a -1 over 180 x to the fourth plus dot, 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 dot. And then my nth term is going to be up the power by 1. So this guy stays the same, right? Up the power by 1 becomes next to the n plus 1, and divide by that n plus 1. So it's going to look like this, right? So that's my nth term. If I want to find c, I realize that f of 0 is 2. Well, notice that when I plug in 0, right, if x is 0, these are all 0, meaning that if f of 0 is 2, that 2 has to be the lone man standing, which is that c. So my f of x is going to be 2 minus 1/10 x plus 1/60th x squared. Sorry, the 1/10 was x squared, the 1/60th is x cubed, I believe. Let me scroll up and check. Sorry, it got cut off. All right, so now I don't actually end up needing the other term. I don't need this guy because I only need the first 3 non-zero terms and the general term. So -1 to the n over a 5n squared n plus 1 all times x to the n plus 1 dot, 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 dot. All right, so that's the idea of how we differentiate and integrate power series, and that's the end of this video.